Welcome to this Blockchain Commons technology overview. Blockchain Commons is a proudly not-for-profit social benefit corporation committed to open source and open development. Our work is focused on building open tools, technologies, and techniques that sustain and advance blockchain and internet security infrastructure and promote an open web. We're funded entirely by donations and collaborative partnerships with people like you. Simply put, our mission is to discover areas where many blockchain and security developers are solving the same problems over and over, and to create unifying technologies that are available for anyone to use. We strive to build technology solutions that are widely applicable, secure, extensible, and always completely open source. We're well aware that attempting to create a unifying standard where there are already 14 competing standards often means there will be 15 competing standards. Unfortunately, a lot of the problems being solved across the blockchain space aren't being standardized or even documented. And in some cases, proposals being promoted as standards turn out to promote forms of vendor lock-in. Blockchain Commons is committed to developing solutions that serve the entire community and ensuring that everything we do supports interoperability. Blockchain Commons also hosts a number of online communities and conferences like Rebooting the Web of Trust, where ongoing conversations take place around new and emerging standards. You'll find all of Blockchain Commons community discussions, research, recommendations, and specifications, as well as the code for libraries, tools, and apps available in our GitHub account. All of our work is open sourced under the BSD 2-clause license. Of particular note is the Blockchain Commons research repository. Each of our research documents begins with BCR, and you'll see various BCRs referenced throughout this video. The first part of this video discusses some important general concepts in the blockchain and security space that we want to make sure you're familiar with, as much of what we do builds on them. The second part reviews several existing technologies that we use as the foundation for our own technology. In the third part, we provide a high-level overview of a number of our core technologies that we have been developing over the past several years. Now we'll introduce some key concepts that underlie our technologies. A seed is a large random number used in cryptography. As the name suggests, seeds are used as the starting point for other things, namely generating useful objects such as keys and cryptocurrency addresses. To make a seed, you need to start with a good source of random numbers, and you need to use enough of those random numbers to make your seed effectively impossible for anyone else to guess. The best random numbers are found in nature, in things like coin flips, die rolls, or thoroughly shuffled decks of cards. Your source of random numbers is called Entropy. Many software programs that generate random numbers have statistical flaws that make them inappropriate for generating seeds. Cryptography-grade random number generators have no known flaws. Tools from Blockchain Commons, like Gordian and Seed Tool, can generate a seed for you using cryptography-grade entropy, or can generate a seed from entropy you provide. Blockchain Commons LithyKit is a standalone hardware tool you can build yourself from standard parts, a 3D printed case, and open source software. LithyKit takes entropy you provide and generates seeds and keys. LithyKit has no storage capability, so all sensitive data is guaranteed to be erased when it is turned off. Having a seed effectively means that you also have everything else that can be derived from it, including your cryptocurrency private keys, so seeds must always be kept secure. Gordian stores your seeds encrypted in your iPhone's keychain. If your device is lost or stolen, your seeds cannot be accessed without your device passcode or biometric authorization. You can also store your key entirely offline on paper as a single printed page, or split into multiple pieces using Blockchain Commons Sharded Secret Key Reconstruction, or SSKR. Blockchain Commons produces KeyTool, an open-source, flexible command line tool that implements a data flow graph for deriving cryptocurrency keys and addresses and signing transactions. Any of the nodes in the graph can be assigned, and any set of nodes can be derived as long as their dependencies are met. Gordian Guardian can also be used to derive keys from seeds. Though cryptocurrency accounts can be protected by a single key, Blockchain Commons advocates for the thoughtful use of multisigs, where an account can only be unlocked by the use of a set of keys. Multisigs are usually said to be M of n, where n keys can be used to unlock an account, but only m of them are necessary. Blockchain Commons' Gordian wallet is built around a 2 of 3 multisig, where any 2 keys out of a set of 3 can be used to access funds. 2 of those keys are kept on separate devices, the Gordian wallet and server, and a third key is kept offline as a recovery key. The use of multisigs is part of Blockchain Commons' Smart Custody program. By requiring 2 keys and keeping them partitioned on different devices, it eliminates the possibility of a single point of compromise, where the theft of a key could result in the theft of funds. By storing a third backup key offline, it also eliminates the possibility of a single point of failure. If either the wallet or the server and its associated key were lost, funds could be recovered with the offline key. Multisigs are a standard Bitcoin Core technology that Blockchain Commons uses in an autonomous way to let users practice responsible key management in order to protect their own cryptocurrency. A number of our technologies address the needs of cryptocurrency wallet developers who create highly secure devices that store or transform sensitive information used to sign transactions like seeds and keys. These devices are usually kept entirely off the internet, often being purpose-built without wireless transceivers for Wi-Fi, Bluetooth, or NFC, or even having a wired connection to another device. All communication with these devices must be done through the Airgap by means of a display and camera. Usually, the data to be transferred is displayed as a QR code that is read by another device. All the Blockchain Commons apps and command line tools we just mentioned rely on a number of underlying technologies. Some of these technologies are already existing best-of-breed solutions, and Blockchain Commons has adopted them as foundations on which to build our community solutions. In this section, we're going to introduce a few of those existing technologies. A Uniform Resource Identifier, or URI, is a unique sequence of characters that identifies a resource used by web technologies. Uniform Resource Locators, URLs, are the best-known kind of URI. They specify the address of a web page that web browsers can interpret, retrieve, and display. However, URIs are more general than URLs and can be constructed to identify anything, whether or not it can be retrieved by a web browser, including email addresses, telephone numbers, and software code repositories. URIs have the advantage of defining a common structure that is easily interpreted by software programs. QR codes are two-dimensional barcodes seen everywhere in advertisements and often in industrial settings. They frequently encode a website URL. Many makers of offline cryptocurrency wallets have settled on QR codes as a way to optically send data through the Airgap between their offline device displays and network-connected devices. Unconnected devices that include a camera can also read QR codes. Exclusively using QR codes for the transmission of data has the advantages of transparency and the elimination of wireless networking and the internet as a source of security risks. QR codes can encode more than URLs. In fact, they can encode any binary data up to a certain size. However, they do not impose an internal structure on the data they convey. There's no standard way for a QR code to display the sort of information it contains, or structure that information. QR codes also have size limitations. The densest QR codes have a capacity of less than 3,000 bytes. This becomes an issue when one wishes to transfer longer data messages, as can happen when, for example, you want to relay a multiple signer Bitcoin transaction to an offline wallet to be signed and relayed back. In addition, since the most common use case of QR codes is usually to convey human-readable text like URLs, the native binary encoding mode of QR codes is not consistently supported by readers. Add to that the consideration that denser QR codes require higher resolution screens to display and higher quality cameras to read. So, in practice, QR codes almost never come close to the theoretical maximum of 3,000 bytes. Nonetheless, the ubiquity and generality of QR codes makes them a good foundation on which to build solutions for air-gapped data transmission that address these issues, and you'll see how we do that shortly. QR codes allow for content to be encoded for easy machine reading, but they don't impose any structure on their content. Structure is important because data objects are often composed of fields that may be present only under some circumstances, or that may be defined and added in the future, or that may contain nested data structures. Some developers have adopted data structuring formats like JSON for the content of QR codes. This has the advantage of being human readable, but at a considerable cost in efficiency, as JSON allows arbitrary amounts of white space around delimiters and encodes every data type as text, from floating point numbers to arbitrary binary data, necessitating the use of secondary encoding methods like base64. Encoding arbitrary text disallows the use of the most efficient QR code encoding methods and makes for inefficient use of the space available in a QR code. Blockchain Commons has adopted the Concise Binary Object Representation, or CBOR format, for representing structured data. CBOR has many advantages, including being space-efficient, self-describing, extensible, and an IETF standard. CBOR enjoys wide language and platform support and requires very little code to implement a codec. QR codes have built-in error detection and correction, and depending on the level of error correction, a significant part of a QR code may be covered up or lost, and the entire code can often still be read correctly. This is how we see company logos being placed in the center of QR codes while remaining readable. However, once a message has been extracted from a QR code into a string of text, it loses any error detection capabilities the QR code provided. When dealing with messages that may be transmitted either as QR codes or text, and particularly when dealing with messages that have been broken into parts, it makes sense to add a method of error detection that applies specifically to the message. For this task, Blockchain Commons uses a 32-bit cyclical redundancy check, or CRC32, that is sufficient to ensure that messages that might be relayed over unreliable means, like humans copying and pasting them, arrive intact. The CRC32 algorithm is fast and widely used. It produces a 32-bit digest or checksum of the input data that is appended to a message. When the message arrives, another CRC32 of the data is calculated and compared to the one in the message. If they match, then it's extremely unlikely that even a single bit of the original message has been copied incorrectly. There is often a need to uniquely identify a digital object, such as a seed or key, without having the complete object at hand. The SHA-256 algorithm produces a 256-bit digest, which is 8 times larger than CRC32. This number of bits provides a number of possibilities close to the estimated number of atoms in the known universe, and provides an astronomically low probability that two different digital objects will produce the same digest. SHA-256 is considered safe for most cryptographic algorithms where digests are compared to guarantee that two input objects are identical. If you wanted to protect a secret, like a cryptographic seed, you could back it up by printing it out and putting it somewhere safe. But anyone who gains access to that location would then have the entire seed. You could encrypt the seed with a password and put the encrypted seed somewhere, but then you might be prevented from recovering it if you couldn't accurately recall the password. An alternative is to secure your secret information in a distributed way. Shamir's secret sharing, or SSS, is a mathematical technique for splitting a secret into shares, each containing some part of the secret, but none that individually can be used to recover the secret. These shares can then be distributed among trustees who you know and that can be trusted to return your shares to you when asked. You can specify a threshold number of shares required to recover your seed. For example, you can split your seed into 5 shares with a threshold of 3. You would then give a share to each of 5 friends. If, at some point, you need to recover your seed, you would only have to successfully contact 3 of those friends for recovery. Blockchain Commons uses SSS as the mathematical foundation for its Shared Secret Key Reconstruction, or SSKR, solution we will describe shortly. When a large binary message is broken into pieces and transmitted, the receiver has to recover every piece or fragment of the message to reassemble back into the original message. If any of the pieces might be missed, such as failing to read one of a sequence of QR codes, the entire sequence must then be retransmitted, and again if the same fragment is missed again. In other words, in a stream of repeating fragments where some of them are lost, it becomes less and less likely that the receiver will get the last few fragments it needs, resulting in stalled transmission. Fountain codes, also known as rateless erasure codes, are a way of producing a limitless stream of fragments from the original message, each of which contain a mixture of the fragments of the original message. By determining what original message fragments are mixed into each fountain code fragment, the receiver can progressively collect and decode the fragments it has into the original message. It can even miss a large percentage of transmitted fragments, and it will still eventually converge on the complete message. A stream of fountain codes has no first or last fragment. The receiver can start decoding the stream at any time and will finish as soon as it receives a fragment containing the last data it needs, which actually becomes more and more likely as more fragments are received and decoded. Now that we've covered some of the foundations we're building on at Blockchain Commons, we'll introduce some of our most essential solutions. Part of the challenge of using QR codes to transmit data via Airgaps is that while they work most universally with text, we want to be able to use QR codes to transmit blocks of structured binary data. Blockchain Commons examined a variety of approaches to encoding binary data as text in QR codes. And we discovered that common methods for doing this, such as JSON and base64, are far less efficient than using a much more restricted character set, for which the QR code standard has a special encoding mode. This restricted character set only includes uppercase letters, the 10 digits, and a few special characters. It doesn't even include many of the characters that are commonly seen in URIs, such as the question mark or pound sign, meaning that an arbitrary URI encoded using these characters will have to use a more general, but less space-efficient encoding mode. Another goal is to be able to encode blocks of binary data like cryptographic seeds as a sequence of words that can easily and accurately be written, read, recognized, spoken, and even memorized by humans. In some use cases, it is even desired that sensitive information like cryptographic seeds or backup shares be inscribed or stamped into metal for long-term survivable storage. Bytewords is a technology specification for transforming any sequence of bytes into a sequence of 4-letter English words. Since bytes contain 8 bits that can have 256 distinct combinations, Bytewords assigns a single 4-letter word to each possible value. The actual list of bytewords was carefully selected to satisfy many criteria that ensure that they are all distinct, memorable, and pronounceable. Among these requirements are that the list contain no homophones or near homophones, and that the first 3 letters, last 3 letters, and first and last letter of each word must be distinct from those of all other words. Additional requirements ensure that a significant number of transcription errors would have to be made to transform any byteword into any other valid byteword. Bytewords specifies that the data encoded using them will always be well-formed CBOR. This provides a layer of structure for any data so that software that decodes bytewords can always assume that their contents will be CBOR of some type. CBOR can contain tags that identify the type of data, and in this sense, Bytewords sequences can be self-describing. In addition to the standard Bytewords format that uses 4-letter words, Bytewords also specifies a minimal encoding of only 2 letters per word, the first and the last. As each byteword has first and last letters that are unique, the standard and minimal Bytewords encodings are isomorphic. Either can be easily transformed into the other. Since bytewords are not case-sensitive, in most contexts they can be written or stored as lowercase and transformed into uppercase without any loss of meaning for efficient transmission in QR codes or when stamped into metal. Finally, Bytewords specifies 4 additional words to be placed at the end of each message containing the CRC32 digest of the message. This provides detection of transcription errors for every Bytewords message. Blockchain Commons provides reference implementations for Bytewords in C and Swift, and provides a command line tool for performing encoding and decoding of Bytewords. Third-party developers have already implemented Bytewords codecs in several other programming languages. As mentioned earlier, URLs and URIs usually name or point to resources located on the web or elsewhere. But cryptocurrency wallet developers often have the need to transmit entire binary objects via an Airgap using optical encoding like QR codes. Blockchain Commons has released a general-purpose URI specification called the Uniform Resource, or UR, whose purpose is not to point to a resource, but to be a complete, self-contained binary resource that is self-describing, structured, and that can be transmitted as a single QR code or block of text, or broken into separately transmitted fragments, either as a unique non-overlapping sequence or as a continuous stream of fountain codes. URs are well-formed URIs. They start with the schema UR:, which is followed by a human-readable type specifier, which may contain hyphens. After the type specifier is the body of the UR, which is a minimally encoded Bytewords message. As all Bytewords messages are also well-formed CBOR, the app that decodes the UR can then use a CBOR library to decode the structured data it contains. You can tell just from looking at this example that it is a UR that encodes a crypto seed type. This type is documented in the Blockchain Commons registry of UR types. Developers can define their own UR types, or, even better, work with the larger community to develop or extend existing types to meet new needs. URs themselves are never case sensitive, and they never use any characters that are not allowed by the alphanumeric QR encoding mode. So, when a UR is transmitted as a QR code, it is first translated to uppercase. When the Bytewords body of the UR is decoded, including verifying its CRC32 checksum, it yields this following binary payload. This is the CBOR message. Decoding this into the more human-readable form of the CBOR diagnostic notation, we have this. This is the CBOR notation for a map, which is a set of key-value pairs. The only key in the map is 1, and the value is a byte string. The definition of the crypto seed type is written in CDDL, the Concise Data Definition language that is part of the CBOR specification, and it tells us how to interpret this map. It shows that the key 1 is the payload, the actual string of bytes that is the seed itself. And it also shows several optional fields that aren't present in this example. These fields can represent the seed's creation date, the seed's name, and some additional notes about the seed. By extending this public information, future additional fields could be added that benefit the entire developer community. URs also provide the ability for larger binary objects to be broken into a series of multi-part URs. Multi-part URs start with the same UR: schema and type as before, but also include a sequence path component that describes the order in which a part appears. A large seed broken down into 7 parts might look like this. As you can see, each sequence component shows the number of this part and the minimal number of parts in the entire sequence. If you had all 7 of these parts, you can always reconstruct the object. However, the magic really starts happening when the UR encoder is asked to continue generating parts beyond the minimum. Now, the UR encoder is emitting parts which are a pseudo-random mixture of the individual parts of the original 7. These are the fountain codes we mentioned earlier. The receiver of each part uses the same pseudo-random algorithm with the part number used to determine what mix of random parts is contained in each fountain code part. Readers can jump into this stream at any point and recover the original message by decoding a number of parts that is, on average, not a lot bigger than the initial sequence of minimal codes. Blockchain Commons maintains open-source reference implementations of the UR codec in C++ and Swift, and third-party developers have already translated it into several other languages, including Python, Rust, Java, and TypeScript. To define a new type of UR, you need a type specifier that appears after the UR: scheme, the CDDL definition for the CBOR, and a numerical CBOR tag that can be used to identify the structure when it's not the top-level object in a UR. Blockchain Commons maintains a registry of known UR types, and is working with the community to define a suite of UR types that solve many common interoperability problems. Blockchain Commons produces LifeHash, an open source method of hash visualization that creates beautiful icons that are deterministic, yet distinct and unique given the input data. The basic concept is to start with a 256-bit digest as a 16 by 16 pixel initial state for running the cellular automata known as Conway's Game of Life. After the pattern becomes stable or begins repeating, the resulting history is used to compile a grayscale image of all the states from the first to last generation. Using Game of Life provides visual structure to the resulting image, even though it was seeded with entropy. You'll find an in-depth video on LifeHash on the Blockchain Commons YouTube channel, and reference implementations in C, C++, and Swift in our GitHub repo. Some objects have metadata that can change, like the object name or notes, without changing the fundamental identity of the object. Blockchain Commons has established a set of guidelines for specifying how to properly make object digests via a digest source specification. Several of our defined UR types, including seeds and HD keys, unambiguously describe how to produce a SHA-256 digest of them that reflects their true identity and not ephemeral metadata. While software programs can easily compare SHA-256 digests, humans often need to perform the same task. Blockchain Commons has published guidelines for laying out an object identity block that includes a LifeHash, an abbreviated SHA-256 hash, and other important metadata. We hope the object identity block will become a familiar visual idiom that helps users across the community quickly identify digital objects of all kinds. As I mentioned earlier, Shamir's secret sharing, or SSS, provides a mathematical algorithm for splitting a secret into multiple shares, including a quorum or threshold of shares that must be reacquired to reconstruct the secret. Blockchain Commons Sharded Secret Key Reconstruction, or SSKR, is an open source library that provides a full implementation of this technology, including an optional two-level scheme with the ability to define several groups that have little or no interaction and that separately hold shares of the secret. In one possible scenario called 2 of 3 of 2 of 3, the owner of a seed defines 3 groups: family members, business colleagues, and professionals like lawyers or banks, and generates 3 shares for each of them for a total of 9 shares, specifying that each group has a threshold of 2, and all the groups together also have a threshold of 2. This means that no single group, by pooling their 3 shares, has the ability to reconstruct the secret without also having at least 2 shares from another group. If the secret owner ever needs to recover the secret, they only need to collect 4 shares total, 2 shares from 2 of the groups. This provides a balance of security and resilience in recovery scenarios for high security secrets. Blockchain Commons Gordian Guardian generates and stores seeds, and can also back them up by printing SSKR shares on coupons that can be distributed to trustees for safekeeping. The object identity block on each coupon identifies the seed that the share is part of, while the QR code on each coupon contains a UR with the SSKR share, and the bytewords printed on the coupon contain the same SSKR in a form that can be easily recognized from the last 4 words containing the CRC32 checksum of the share, and that can even be read aloud over an audio connection, if necessary. Torgap is the Blockchain Commons security and privacy architecture model for creating gaps between network-connected apps and microservices. Torgap supports privacy, service anonymity, identity pseudonymity, non-correlation, censorship resistance, and separation of interests, and reduces single points of failure. This emerging architecture is supported by QuickConnect and Blockchain Commons Gordian system, while our Airgaps wallet community and our research papers are charting its future. We hope you've enjoyed this tour of some of the exciting solutions we've been working on at Blockchain Commons. We are entirely community supported, so please contact us to discuss ways we can work together to make solutions that benefit your project specifically, as well as the community as a whole.